The more sophisticated your test is, the more assumptions you're going to have. And literally, it takes about 5 times as long to check the assumptions of the data than it does to run the test. What am I missing here? I screwed up on my PowerPoint. I don't know what this is. Please hold. T-tests, ANOVAs. Oh, there it is. Okay, I did not. I take that back. Please hold. From current slide. All right, so correlations. So the second half, the relationships part. If you're looking for relationships, and I suggest you do all, you make it a mixed salad bar. Look, run a couple t-tests, couple of ANOVAs. Always have some kind of grouping going on. It comes from your demographic variables. But also have some kind of correlation. Is there a cause and effect between the length of time a person's getting therapy and if it indeed lowers their depression scores or something along those lines, right? So again, try to put as many of these tests in there as possible. These are the types of variables. These are the types of correlation. And I'm sorry about all the flying around stuff. This must be an old one because I don't like the flying around stuff anymore. I liked it when I first came out, but now it's just kind of boring. But now correlations, right? Relations is right in the word right there. Correlations. Co means two. So if you're going to look for a relationship between two variables, you're going to run a correlation. And there's a half a dozen that we use here. Pearson's is the number one that we use. And regressions are based on correlations, okay? And then you got your linear regression, which is also called a simple regression. Multiple regressions, that means you got a lot of IVs, and hierarchical, and there's stepwise. It goes on and on and on. So, but again, we have everything covered. And the last one I'm going to talk about right now is the chi-square test. I never know where to put this guy. It looks for relations or actually associations between two categorical variables, right? And there's two of them. There's a test for independence and there's a goodness of fit. So that's it right there. That's it in a nutshell. And if your data is a mess, which it's going to happen sometimes your data is a mess. In other words, it will not pass the assumptions of your data. Then you have to switch to the non-parametric tests, of which chi-squared is probably the number one. But the difference between a non-parametric test and a parametric test is simply that one uses means and the other one uses medians, okay? Non-parametric test uses medians, okay? Now, what I'm going to do is version 26 is brand new. You guys can get that for free. It is an Alliant free service. What you do is you contact the IT department and just tell them, I would like to download SPSS onto my computer. They send you a form that you have to fill out. Once they verify that you're an Alliant student, and then they send you the download link, et cetera, et cetera. If you have a Macintosh or an Apple, there might be some issues, but the IT guys are sharp. They'll walk you through it. So let's just jump right in it. Okay, t-tests. Here we go. I'm gonna switch over to SPSS. If you got any questions, just stop me. Everybody good? So here's SPSS. And so here's all your variables, right? This is the date, this is the variable view. SPSS has two parts. It has a variable view right here and a data view. The data view looks more like the spreadsheet, Excel, right? This is the one with all the numbers in it. And the variable view describes the variable. It's got the variable name, and you have two options. You can name the variable. This is what SPSS will know the variable as, but the labels, you have your option in the output. You can have it show up. The output could be either in labels or the name of the variable. And here's a big hint. If you have values that are numbers that are labeled here, right, here's ethnicity. 1 is white, 2 is Latino, 3 is African American, 4 is Asian American. That automatically makes it a nominal variable. So SPSS only recognizes 3 different variables: a scale or continuous variable, it's a regular number, An ordinal is a Likert scale type of thing, right? Where 1 is never and 5 is always, that kind of thing. That makes it an ordinal. And a nominal is a categorical or grouping variable. So let's do a t-test. I'm going to do a one-way t-test. In other words, I'm going to take a single sample, a small sample out of a population, and I'm going to compare that sample mean to the stated population mean. In fact, I got a little practice test if you guys want to cheat. I made this for the clinical PhD program a couple years ago, and it's basically, it has every test that they've ever had. I made my own test, and then there's an answer sheet that shows you how to get the answers, and there's videos embedded in the answer sheet. So if you want to walk through how to run a chi-square test, t-test, ANOVA, regressions, all that stuff, this would probably be a good place to start. And again, this is in the Hawk 2 and the Hawk 3, so don't let today be the only thing that will show you how to do this stuff. Again, all of this stuff is online. We got a ton of videos. So number 4. Make that so you guys can all see it. I am going to check from my sample size, from the stated norm. So a stated norm is from the population, okay? Stated norm is 278, average. Standard deviation is 12.15. We're gonna check our one sample against 278. Now this goes fast, okay? These tests are actually fast. You're gonna go to analyze. That's where you live. You live and analyze. You're gonna go to compare means. And it says one sample t-test. Skabam. And our variable we're testing is weight. The test value is 278. That's what we're testing it against. Always check your options. Nothing there. Click OK. You're done. Okay. So there's the descriptions of the data. There's your sample size. So the mean from our sample was 285.7. And what this is saying is that the bottom thing here, I don't think I can make this bottom one bigger. Sorry, hold on. Let's see if I can. Nope, can't. But this one says your t-score is 2.719. What that literally means is that the distance between the stated norm, the stated mean from the population of 2.78 and this sample mean of 2.875 is 2.71 standard deviations away from each other, and that is considered significant because the significance is less than 0.05. So in other words, you just showed that your sample is significantly heavier than the stated norm. Simple. One sample t-test. Moving on. Let's do a two sample t-test. Right? A two sample, also called an independent sample or just an independent t-test. We're going to check to see if there's a significant difference in effectiveness scores. So, right, the DV is whatever you're trying to see if there's a difference in. We're going to look at effectiveness scores between managers and staff. Okay? So from our variable position, managers and staff are number 1 and 2. So again, we go to analyze, compare means. This one is an independent sample. So the test variable is your DV, and what did we say, effectiveness scores? And then our grouping variable is going to be the categorical variable of position. You have to define them. So we said 1 and 2 only, even though there's more than 1 and 2 options. And nothing there, click OK, boom. So there's the means of each group here for their effectiveness score means. The managers were about 11.6 and the staff was 8.7. There's a big difference there, right? And that's what it's looking for. Is the difference big enough to be considered significant? So you drop down to the output box here, independent samples. And the short answer is you simply look at the t-score. If it's greater than 2, on average, a rule of thumb, If your t-score is 2 or greater, you're going to have a significant difference. And you do, okay? This is less than 0.05, therefore, that means that there is a significant difference in effectiveness scores between the managers and staff. Am I going too fast? I know this can get kind of boring unless you're a nerd guy like me. So this first part of the t-test, you'll notice says Levine's test equality of variance. That's one of the assumptions of a t-test. The variance for each group should be relatively the same. And remember, variance is a mathematical calculation that you have to subtract every individual piece of data from the group mean, square them, add them all up, that kind of stuff. So that they have to be relatively the same. And this says that they were, right? It did not violate that assumption. Let's do one more t-test. And that is a paired t-test, I'm pretty sure. So we're going to run a paired t-test. A paired t-test is like a pre and a post. There's only one group, but there's 2 measurements. The other kind of t-test, there's 2 groups, 1 measurement, but a paired t-test is there's only 1 group and 2 measurements. So we're going to see if there was a significant difference in the number of car sales between April and June. Okay, April and June. So we go to Analyze, Compare Means. There it is right there, Paired Sample T-Tests. And it says, what are you comparing? And you're going to pick April as number 1. And then the second measurement one is in June. And again, I don't think you need anything up there. And you click OK. And here's your means, right? April was 7.6. June was 9.9. So there is a difference. But you're never sure if it's significant or not. There's always a difference. But you're never sure if there's a significant difference or not. So you go down here to the output table, paired samples test. And there's the difference of the mean. There's your t-score. So in -2, it doesn't matter if it's negative or positive. T-scores are actually, we're supposed to use the absolute value of them anyway. But you'll notice that even though it's 2.044, it wasn't quite significant. It's not significant until this sig value, which is the same as a p-value, is under 0.05, and it's not. It's close, but it's not significant. So in other words, according to statistics, there was no significant difference in the average auto sales between April and June. That's a lot we just went through, you guys. We're going to move it on up. I'm going to show you how to do a one-way ANOVA. It's actually what we call a one-way between group ANOVA, which is just like the t-test, except for it allows you to compare more than 2 groups. You could do 3 groups. You could do 10 groups. You could do 100 groups if you want. Don't do 100 groups. That's too much. But it does the same thing. It looks at the means, and it uses some math calculations to see if the difference between the means is large enough to be considered significant. So in this problem, we have a variable named hospital, which is a grouping variable. So there's 3 different hospitals. And then the DB is age of detection. Can you guys hear that? Is that just me? Am I hearing things again? All right, back to it. All right, so we're going to run a one-way between group ANOVA. Hospital is our categorical variable. Age detection is our dependent variable. So we go to Analyze. And there's more than one way to do this in SPSS. But do it my way, because my way is the best way. You're going to go to General Linear Model. Univariate. Univariate means 1 dB. All ANOVAs only have 1 dB. All between group ANOVAs only have 1 dB. You can have more than 1 dB, but that ANOVA turns into a MANOVA. Okay, that's what this is, multivariate. But we're only doing 1 dB. And hospital was our grouping variable. That means factor. Age of detection is our dB. And what you do is, until you know what you're doing, look at all these buttons, okay? Because there's a lot of options here that will look at your assumptions for you, so you don't have to do them separately. It's all rolled up into the same test, which is a big time saver. And we're not doing contrasts. We're not doing plots. We should do a post hoc test. I prefer the Tukey because I like the way it sounds. Not really. The Tukey is the least restrictive. So if there's a borderline significant difference, the Tukey test will give it to you. Some of them are very, very restrictive. So, and options. So this options box is actually a pretty important one here. We always want the descriptives, the effect size, the power, and the homogeneity variance tests. Never bootstrap, because I don't like it. Bootstrap to me is an act of desperation. Most people only use bootstrapping if they don't get significance on their first try, then they try bootstrapping, which to me is like cheating, so I don't do it. But you'll notice when you click run, it comes out nice and neat on your output. Okay, so there's two different SPSS files. One has all the data. It's this one, right? This is called a .sav file, right? SAV means the data is on it. And the other one is SPV. It's this one. It has all the charts and the output on it. So remember, P stands for output. All right, back to work. So here's your sample size. How many people were in each hospital? Okay. They're not quite even, but they don't have to be. They're their median ages right here. Their mean ages, and there was, I see a 23 and I see a 27. So there was a pretty good difference. There's a difference of about 4 years. And when I teach this class, I always tell people to try to gauge that right off the bat, so you don't get surprised when you read the output. This right here, this tested between subjects box, this is your main box. It tells you right off the bat if your model was significant or not. So this corrected model row and this hospital row should be identical because you only got one IV, and they are. Now, according to this, the significance is 0.295, which means that the difference was not significant difference. Again, even though there was a difference in their means up here, the difference was not large enough to be considered significant, and that's what this F score says. So the F ratio is the ratio between group variance, which comes from the grouping, and within group variance, which is what we call an error term because it comes with the data. There's nothing you can do about that. Okay. And since there was no significant difference here, we don't care about the post hoc test. Okay. So again, if there was no significant difference in the first model, don't bother looking at the post hocs because there won't be anything in there. How are we doing, you guys? Getting kind of quiet out there. All right. So now we're going to do the second kind, the within group ANOVA, also called the repeated measures. I prefer the name repeated measures because it kind of explains what it does, right? The measures are repeated more than once. Think pre and post test. Whenever you're talking about repeated measures within group, think pre and post, and then maybe like a follow-up test 6 months later, another follow-up a year later, that kind of stuff, okay? So now we're going to see if there was a significant difference between the pre-test. Looks like we got 4 timed measurements and then a follow-up. And we're looking to see if the sexual harassment sensitivity program was effective at reducing the number of complaints from the company, okay? So let's go ahead and look at the data. So here they are, pre 1, 2, 3, 4, 5. So this pre is how many of the, there's 1, 2, 3, 4, 5, 6, 6, 2, 1, 2, 3, 4, 7, 7 different companies. They're all part of the same company, 7 different offices in 7 different cities. And this is the number of harassments that they got before they did any kind of training. So after the first week of training, This was their number, right? You can see it going down a little bit for some of them. This is after 2 weeks, 3 weeks, 4 weeks follow, and then the follow-up 6 months later. And you can see that they did go down from the beginning. But again, we're going to let the computer do the talking here. So to run it within Group ANOVA, you're going to go to Analyze, General Linear Model, Repeated Measures. Factor. Since normally, and not always, but normally there is a time segment between measurements, I always name this guy time. And how many different times do we have? It looks like we have 6. And now we have to define them. And we're going to go down here. We're going to say pre was number 1, 1 was 2, 2 was 3, 3 was 3. Boom. And then we don't care about model, plots, don't care. Well, let me put plots in there and show you what it looks like. Some of your teachers are going to want to see plots anyway. Post hoc, nah, we're not going to do post hocs. Options, yes, we'll always do the options with the ANOVAs. Descriptives, effect size, power. And homogeneity tests. Okay. So the first thing I look at is I always look at the means. Oh my, yes, there is. I predict that there's going to be a significant difference. Because if you look at the post-test, the average is 54. You look at the pre-test, it was way up there at 67. So it dropped 13 points on average between the 7 stores. That's quite a bit, so I would bet money that there is a significance. Multivariate tests. Do not look at this now. It will come into play here later. Sphericity, that's one of the assumptions. But here's the money box again. This is your ANOVA box. So your test of within subjects ANOVA box, you got an F ratio of 50.89, which is huge. That's huge. Which in turn gives you a little tiny probability value, or the sig value. And this is actually, we can't write that the sig value is 0.000. We have to write the sig value is less than 0.001. Okay. But what that means is the probability that this happened by chance alone is nothing, roughly. So in other words, that's when you reject the null. The null states there's no significant difference between these measurements, but this says that the probability, the percentage that the null is true is about 0%, therefore you reject the null. Okay. So there was a significant improvement in the number of harassments over the year, over the training. So whatever the training did seemed to work. So you paid a guy. Okay, here we go. So I just went through one whole semester of statistics in about 20 minutes. Yeah, so any questions so far? Anybody, anything? Nothing coming across the
Rich,
chat?
we're getting not so much questions about your presentation. It sounds like we need to go back to the toolbox and ensure one of the video recordings isn't coming up properly. So we'll need to do that. But yeah, no questions so far in your presentation. Good stuff.
Yeah. Well, thank you. And when it comes to the Moodles, you let me know if one of the videos isn't working properly. Okay, the school switched, they upgraded the Moodles, and I had to hand set all the videos back again. And I keep thinking I got them all, but every once in a while I run into one where I didn't. So yeah, if you can find, go ahead.
Yeah, Rich, it was the one from Aaron Draper, the APA, where that was the one where I sent you the link, and then it had the passcode, and you're like, oh, can we do this without the passcode? And I said, oh, we need to look at the Zoom site, figure that out. So that one doesn't seem to be sure.
I will investigate that, you guys. I will. That really isn't one of mine, but I'll investigate it anyway. It's usually some kind of weird setting on Google.
All right, thank you. See, Tanya, we'll get it up there for you. Thank you. All right, keep going, Rich.
Thank you. Sorry, wipe down. I'm really in a shed with the lights on. It gets kind of warm in here. And one of my grandchildren might be bursting through the door any second, so. But they're so darn cute. You guys know them anyway. Okay, here we go. You know what? I'm going to skip the harder ones because, yeah, you don't need the harder ones. Not at this time, right? These are the mixed ANOVAs, and, you know, they go on and on and on. Let me do a MANOVA. A lot of people do MANOVAs. That means you're measuring differences in more than 1 dB, okay? So in this problem, we have 2 variables. One is the drug dose, and it has 3 levels. One was the control group. One got 10 milligrams. The last group got 20 milligrams. And the second variable is smoothie size. It's a health smoothie. One is a small and one is a large. So you got 2 categorical variables there running at the same time. And you want to see if there's a significant difference in the number of push-ups between the drug dosage sizes and or the smoothie sizes. And then the second part of that is you want to see if there's a significant difference in the number of sit-ups between the drug dose sizes and the smoothie sizes. Okay, so there's a lot of math in there. And the beauty about running a ANOVA is you can do it all at the same time. You could run single ANOVAs, but remember, the more tests you run, the higher chances of you guys making a type 1 error will be, right? The more tests you run, the higher the probability that you're going to make a type 1 error. Okay, so, but it's again, everything's under analyze. You're going to go to general linear model. This time we're going to switch over to multivariate. That means more than 1 dB. And this is the push-up one. Yep, we got push-ups, we got sit-ups, and drug dose. Remember, there's 3 subgroups. Those are called levels of drug dose, and there's only 2 for the smoothies. This is all default. Leave that one alone. Contrast, no. Plots, we could do some plots. Let's see how they work out. Now, with a 2 categorical factor ANOVA or MANOVA, you're looking to see if they interact. In other words, perhaps those rats, these are all rats, the rats that got the high dose of the drug and the large smoothie did a lot more push-ups, right? So that interaction between the 2 IVs, that's what you got to look for in a factorial ANOVA. And we're not going to worry about post-hocs. Excuse me. Go. So if it doesn't line up right, you see, oh, there it goes. Sometimes the longer test takes a little while. But this thing on the side here, if you want to go back and check a previous test, you can say, you know what, I want to go back to that ANOVA, and it brings you right up here. So this little slide bar is actually kind of a huge time saver. But these are the groups, right? 3 for the drug dose, 2 for the smoothie size, how many in each group. And here's the statistics right here, the means. Oh yeah, there's obviously a difference. I see a 3 here, right? Push-ups. So the group that got the 10 milligrams and the large smoothie only did 3 push-ups. Bunch of weaklings. And then let's look for some big, oh, there's a big number right there. The ones that got the 20 milligram and had the large smoothie, they did 23. So there's obviously a significant difference in there. But again, we could scroll down to this one, the test between subjects. So first of all, we look at the rows. Every row is a variable, right? So the categorical variable, a drug dose, here it is right here. And then there's the dV for push-ups and a dV for sit-ups. So you simply scroll along until you see the F column. So the F column right here is 60. That relatively means that the variance, 60 times of the variance is coming from between the groups as it is within groups. So in other words, something about those groups are making a change. And the significance is less than 0.05. So this is when we say, oh yeah, there's a significant difference in the number of push-ups based on drug dose, also called there's a main effect of drug dose. Main effect means there's a significant difference between the levels. Now we go down to sit-ups. Same thing, right? The sig value is less than 0.05. So therefore, there's a main effect of drug dose based on sit-ups as well. That's good. Now we look at the second variable, smoothie size. So this first row is the number of push-ups. Remember, in smoothie size, it's actually a t-test. There's only 2 groups. But the ANOVA table will run it as well. So you go over here, the F ratio is only 1.36. The p-value is not less than 0.05. Therefore, there was no significant difference in the number of push-ups based on smoothie size. Another way to say that, there's no main effect for smoothie size. And let's look at sit-ups, same thing. Sit-ups, there was no significant difference. So in other words, smoothie size by itself had nothing to do with the number of push-ups or nothing to do with the sit-ups. The smoothie size by itself had no effect whatsoever. But here is the important row. That little asterisk means this is checking for interaction. And what it does is it pairs every group and reruns the data. So it'll take the no dose and run a t-test between the large and small smoothie. It'll take the medium dose, run a t-test just for those guys. It'll take the high dosage group and run a t-test between large and small. Same thing. That's what it does every possible pairwise comparison. And then the other way, it'll run a separate ANOVA strictly for the small smoothie and then a separate one for the large smoothie. Wish I had one right now. Blueberry and banana. Oh, yeah. So that's what this asterisk means. So, look at that. The asterisk on push-ups means there's a significant interaction. Okay? Same with sit-ups. Now, this is kind of a difficult thing to explain here, but what it means is at least one of the levels of the dosage, the drug dosage, is interacting with at least one level of the smoothie. So the smoothie by itself didn't do much of anything, but when you link the smoothie up with one of the dosages, it does something, right? It does cause more sit-ups. So it's more like an additive to whatever your push-up drug is, right? And if these lines cross, these are the graphs of the means. If they cross, which they do, that tells you that there's interaction as well, right? Crossing of the estimated marginal means. So it looks to me like the most potent one would be the drug, right? 20 milligrams. The more drug they get, the more push-ups they did, except for the 10 grams, right? This shows you, right? So the ones that had 0 drug, the control group did about 9 push-ups. The group that got 10 milligrams, they did about 3 push-ups. But the ones that got 20, man, they did 20. So the drug does work, but in large amounts. You need to really drug up them rats. Don't drug up the rats, you guys. Don't drug up the rats. All right. So that was it for the differences. Okay? And again, there's a lot of variations on these types, but again, we got you covered in everything. I'm going to try to show you that in the last 5 minutes. Let's do some, let's just do some correlations. And all right, I'll come back to this. So correlations are kind of easy. They're like the basics. Let's just pick a couple of variables, and we're going to analyze again, correlate. Bivariate means 2 variables. The variables should be continuous variables, scale variables. And I'm just going to pick depression and, I don't know, age. So, does age affect depression? Possibly. Does depression affect age? Not possible. So it's not always easy to tell what's the cause and what's the effect here. If there's a correlation, it's not significant, so it doesn't matter what the number is. Got it? I'll say that again. If it's not significant, Don't worry about what the number says. It means it's not significant, and you haven't proved anything. Okay. So that's correlations. Let's do a regression. Regressions are more likely what you're about to use. Where do you go here? All right. So we're gonna conduct a simultaneous multiple regression, which is also known as a standard regression. Different books call it different things, but it's the most common type of multiple regression that most people run. So we're going to try to predict how many times a celebrity has been married. That's the DB. We're trying to predict an outcome. So if you hear the word predict, that means you're going to use a regression model. So we're going to try to predict how frequently somebody gets married, a celebrity gets married, based on their monthly income, the number of previous romantic relationships, and the number of parties that they go to a month. You know, celebrities, they have to be seen with the right people at the right place. Okay, so let me show you how to do that. Get back to your... Now, here's the beauty. So here's the output sheet. There's the data sheet. You can go to analyzing either one of them. Doesn't matter. So with this one, we're going to go to regression, and we're assuming linear. And where'd you go? Where'd you go? Where'd you go? Oh, you're way down here. There we go. So marriage frequencies, that's what we're trying to predict, right? We're trying to come up with some kind of prediction equation based on how much money they make, how many times they've been in love, and how many parties they go to per month. You know, stats teachers go to parties practically every night, so. Just seeing who's awake out there. Who's awake out there? Okay, we go to statistics. And I'm doing this on automatic. I've done a million of them. So you always do the right side here. And the Durbin-Watson. Continue. Plots. Now all this little sidebar stuff, this is going to check your assumptions for multiple regression. Save. We need to check for multivariate outliers. Options, no, nothing there. Don't care about this. So this is your regression. And the first thing it gives you is the means and standard deviations, which we don't use here, so they don't make a difference here. Correlation box, really don't need to look at that too. I can see that there's significance all over the place, but we're going to let the output for the regression tell us. You know, not all of these IVs might be good predictors. You just don't know until you look at the output. But this is the first thing you look at is your ANOVA. Your ANOVA will tell you, is your regression significant? Yes or no. And because it's less than 0.05, that means you get to reject the null. So the null in this one is, no, nothing predicts marriage frequency. These variables will not predict marriage frequency. That's what the null states. You get to flush that null down to statistics, John. Boom. And you're going to say, yes, these do predict. At least one of them does predict. That's what this means. And then you jump up here to your R square. That's your effect size. In other words, effect size is the percent of the variance that you can explain with your variables. So in other words, you can explain almost a third of the percent of your marriage frequencies simply by these three variables, which, believe it or not, is actually really high. So it means you've got a really, really good model. And then you go down to your coefficients box, and you'll notice these are your IVs. So your first row, monthly income. Don't look at the B weight. Look at the beta weight. The beta weight is the standardized, it's like a correlation. So the standardized correlation between monthly income and how many times they've been married is roughly 0.576, which is incredibly strong, and it's significant. Got it? So that tells me that monthly income is a good predictor of how many times celebrities will be married. Number two, the number of previous relationships. And I scroll down here, the beta weight is close to 0. So it means, and it's not significant. So in other words, it means the number of times these guys get married has nothing to do with how many previous relationships they had, right? And then the last one is the number of parties they go to. Same thing, the beta weight is close to 0. The sig is nowhere near under 0.05. So in other words, the only thing that predicts from this model is how much money they make. Money, money, money. Dirty, filthy money. Oh yeah, and then we would do this. And we would do that. I'm checking one of the assumptions here. So what you're looking at here, this weird looking little line, that's called the lowest line, and it'll tell us if it violated the assumption of homoscedasticity. There's your college education for you. And it looks like it did a little bit, but nothing to write home about. So let me get back. I think that's all the tests that I wanted to show you. Oh yeah, let me show you a chi-squared real quick. So chi-squared, remember, it compares two categorical variables. So let's say we want to check, do Republicans tend to be male? So your first categorical IV is political party. You got your Republicans, Democrats, other. And then your second IV is gender, male or female. So we're going to go to analyze. It's weird. So SPSS is I believe it was made in England. They're British. And they call chi-squareds crosstabs. So to find it, you go to Analyze, Descriptive Statistics, Crosstabs. Get in there, you. And we're going to put in political party and gender. And we don't care about that. We do care about the chi-squared test statistic. We use the phi and the Kramer's V to be like effect sizes. They'll tell us the percent of the variance that can be explained. And personally, I like to look at the expected cell count if the null were true. So in this test, the null would state that there's exactly the same amount as men and women in each of the party. That's what the null states. There's no difference between gender and party. That's what the null states, and we're going to see if we can't shoot that down. And then we also look at the standardized residuals, because if there is a significant difference, this will tell us where it is. Don't care about the rest of that stuff. And there's the means. Okay, the count is real count, observed, people really there. Expected is if the null were true. So in other words, we expected 40 Democratic females, and we got 41. Pretty dang close. So there'll be no significant difference here. And then you go down to the chi-squared, Pearson chi-squared test, and the p-value is sky high, which means that there is no significant association between gender and political party. Again, I just made up this data. So, all right, I'm rounding this out here. Let me finish the PowerPoint. Where is this? Here we go. So we did that, did those, did that, did this. Oh, so everything that I did, I've been putting this stuff together for at least 15 years. Between me and all the teachers and all the tutors that I hired, we have so much stuff already online on how to do everything. And they're in the Hawk Moodles. And the Moodle, how to get to the Moodle is elearning.alliant.edu. And I'm going to try to take you there real quick. And again, we got hundreds of video tutorials. They're self-enrolling. Okay? They're accurate. They're comprehensive. We have everything that you guys would ever need in here. And it breaks down like this. Hawk 1 is basic stats, which if you guys are dissertation level, probably don't need that. Number 2 is differences. So that's t-tests and ANOVAs, and ANOVAs, and ANCOVAs, et cetera, et cetera. Number 3 is relationships. That's regressions. Anything built on a correlation. Comp reviews, you guys don't need that. Okay, the dissertation toolbox, Hawk 5, it has a lot of other stuff besides the stats. So the stats part in the Hawk 5, it'll just link you back to the Hawk 2 and 3. But it also has a ton of APA formatting, how to write a literature review. I strongly suggest everybody check out the dissertation toolbox, Hawk, because I just keep adding to it. It gets better and better and better. Okay, questions, comments?